record.
Wonderful.
Oh,
there you go.
There we go. I don't know what I do with that file after it's all recorded, but
let future Jason worry about
that. Okay, we'll try and share that out somehow. And it's actually a good thing to know for sorting out anything in the future. So just a quick recap, because we only just pressed record right now. I talked about the basic function of the L293D chip, taking a weak signal from the Arduino that comes in right here on the input pin, amplifying that to the output pin right here. When the Arduino signal goes high, then that enables this line coming out right here to be connected in through this pin on the chip. It comes right around here and it's connected to our big battery right here. So we've got lots of current that can flow into the chip because this pin is high from the Arduino. The current from the battery flows out here, comes out to the motor, through the motor, causes the motor to turn, because the motor can then return its current right through the green line right there, comes to the output pin on the L293D, which allows it to sync to ground because this pin right here has been driven low by the Arduino pin that controls it. So the Arduino pins, although powerful for a logic device in terms of what they can provide current-wise, can only provide 5 volts at 40 milliamps, and our motors need a lot more power than that to turn. So the L293D is allowing our Arduino to amplify its power to control the motor. By changing which pin is high and which pin is low coming from our Arduino, we can change whether this signal is high or this signal is low, thus allowing us to change the direction that the motor rotates in. Or if we set them both low or both high, we can turn the motor off. As the motor is spinning, what we've got right here is actually a gear motor. So there's a planetary gearbox in this gray box right here. On the back side of this is the actual motor. And on the far back side of that, we would have a small disc that's spinning around with an optical sensor on the back. There would be an LED that transmits light through slots in the disc, and a phototransistor or photodiode that would receive those signals. So what we see happening on the purple line right here, which is triggered, labeled output A, is as the motor is spinning around, the disc that's attached to the motor shaft is flying around, and there are slots in that disc that allow light to transmit to the photodiode, and the photodiode comes up here and turns the photodiode or phototransistor turns on or off. And when just a minute, let me just move this over here so we can see the Arduino. We've set this pin on the Arduino to have what we call a pull-up resistor on that. You'll recall we talked about pull-up resistors back before spring break, and we use them for our switches on our Arduino control board because they're just a little resistor inside of our Arduino chip down here, a 10K resistor, in fact, 10K ohms, that just provides a little bit of positive current right here, unless there is something else dragging it low. And when light transmits through the disk and hits the phototransistor turns on and drags the signal in this purple wire low. We see the result on the oscilloscope because the oscilloscope is just like a multimeter, but it has a timeline along the bottom right here. We're actually seeing a graph. The vertical axis is measured in volts, and the horizontal axis is measured in time. And if you right-click on the oscilloscope, you can actually change the time division here on the bottom. And so the first time you use the oscilloscope, it might not have the right time division. If you have too large of a time division, so if we take a look at that and we have 1 second across the bottom right here, you'll see these pulses all come in so fast. Oh, that caused it to stop and think about something. Let me just stop that simulation. I'll restart the simulation. And we should see a completely blurry line, like a solid line coming right along in here if everything's running fine. The motor's running right there, and it should be turning so fast that we can see it. There we go. So you can see in here now the signals are coming in so fast that we're hitting a rising edge, a falling edge, a rising edge, a falling edge. And we need to change this time scale along the bottom. And we do that by right-clicking on the oscilloscope and coming in here. And we can change our time frame down here. So now we're seeing 1 millisecond for each of these divisions right here. Key terms that were, and that just changed because my program changed the speed of the motor. I'm slowly speeding the motor up as we come along here. And key terms that we have looking at the waveform is we have a rising edge, we have the high period right in here, we have a falling edge, and we have the low period right here. And by the time you incorporate the rising, the high, the falling, and the low, you have one complete waveform. And by timing that waveform, we can tell how fast the motor is running. By counting the number of pulses, we can tell how far that disk has traveled, and we can watch and we can measure how far the motor is turned. So that brief recap, making sense? Sounding good?
Yep.
Okay, good.
Yep.
So now what we need to do is we need to have a way to count these pulses as they come into our Arduino. Now, one way that you could do that is just go into your main loop, and let me bring up some of my code right here. And oh, that's going to look pretty tiny, isn't it? Is that legible at all?
Yeah, it's not bad.
Okay.
Oh, okay.
If you're full screen, it's all right.
Okay. What we've got right here is, of course, we've got our void loop. Now, using the coding tools that we have without using interrupts, you could use what's called a polling technique in here, where inside your void loop, you could do nothing but check and see, is this signal high? And then if you say it's high, then you can say, okay, wait until it goes low. And then you can say, wait until it's high again. And then you can count one full pulse. So if you didn't want to use interrupts, you could take your loop right in here, and just using digital read, you could come in here and you could say, okay, digital read says I'm low, says I'm low, says I'm low, oops, says I'm high. Okay, good. Wait until that digital read says I'm low again. Keep reading high, 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 low, bang. Now I've gone one full pulse, and you could increment your counter by 1 and print that number out. And you'd be able to say I've traveled one loop. But your program wouldn't be able to do anything else during that time, because it would be so busy going and polling that interrupt to make sure that it didn't miss that falling edge or that rising edge. If you had, there I just changed the speed of the motor. The code's got a for loop in it that changes the motor speed. Now it's speeding up a little bit. The pulses are getting faster and faster because the disk is spinning faster and faster. So it's spending less and less time with the light transmitting through each slot on the disk. So what we've got now is, I wanted to introduce the concept of the interrupt, because it is an exceptionally powerful programming technique. And what happens with your interrupt is that you use this line of code right in here, the attach interrupt command. And that enables one of the background features of the Atmega chip that we're using. Each of the microcontrollers that are used in a huge range of projects has their own data sheet and their own set of rules, but they have some standard things between them, and they will all have some form of what's called a hardware interrupt. Now, normally when your code is running in right here, each of these instructions is compressed into a little digital code that the computer understands. And so the computer won't see a for statement, but it will see a memory location for your variable here, and it will see a command to test that variable, and it'll say, well, if that variable is less than 255, then do these steps. If it's greater than 255, jump down here and do these steps. And you can think of each of these as having the equivalent of a line number. So this might be line number 1, 2, 3, 4, 5, 6, 7, 8, 9, right in here. And they're actually the memory locations of that part of the code. And each time it executes a command, there's a place in memory that increments a counter so that it knows, okay, well, I've incremented line 3 or whatever. Actually, we could just use these numbers right out here to say which line we're in. Oh, that was kind of cool. You know, we're in line 20. Let's now go ahead and execute line 21. And it'll go through and it'll execute each of these lines right down here. And in our normal operation without interrupts, it will just keep going through and following that normal sequence. With interrupts, though, what happens is when we've told it to watch for a rising edge. So there is a part of the chip in the background that just kind of keeps its ear out and listens to interrupt 0, which is on pin 2 on this particular chip. It listens to that, and when it hears it go high, I'm anthropomorphizing too much, but when it goes high, it says, aha, my interrupt condition has been met. And inside the chip, it says, okay, remember that I'm on line 20, but when an interrupt happens, it says I'm supposed to run memory location, the code in memory location known as encoder A, and it drops down here and it executes code starting at line 29 right in here, and it runs this code right in here. It zips through right there and then comes back right into here.
Jason, do you mind quickly explaining what that encoder A is saying?
Okay, so in encoder A, what we've got is we've got a variable called encoder ticks right here, which I defined up at the beginning of the program as an unsigned integer variable, which is fine for our code. We might, if we're going to make it go forwards and backwards, we might get rid of the unsigned part because we might want to be able to use negative numbers. So if you'll recall, an integer variable can hold whole numbers between 0 and 65,536 or something like that. 0 and 65,000, we'll say. If we get rid of the unsigned part, we'll have an integer variable, which can hold just as many different numbers, but because we want to hold negative numbers in a signed integer, it'll go from minus 32,000 to plus 32,000. So we've got two different things we can put in there. And if we need a bigger number, then we can go to a long type variable, which will use 4 bytes of memory. It'll take a little bit longer to process. And in that time that it takes for it to process, then what we're going to see is I just got distracted because something went beep on my email, and I'm just wondering if I've got somebody stuck who can't get in here and they're emailing me to say, let me out of the waiting room. I don't think so. I think everybody's in, so it's probably not that important. Sorry about that. Anyway, so the unsigned long is just a bigger variable that can hold a bigger number. So I've got this variable called encoder ticks, and what that's going to do is that's going to count how many of these pulses I see coming through right here. So when we come down to this code, I'm going to say encoder ticks plus plus is the shorthand way to say, I need to stop the simulation right there, and I can add a comment in right here. Increment so we're basically just adding 1 to that variable because we've seen 1 more pulse come in. Now, the other 2 parts I've got in here are not what you'd necessarily do for right at your beginning. These are for measuring speed. And I wanted to see if I could get TinkerCAD to measure the speed that the pulses were coming in at. So what I do right here is, you're familiar with the millis command. I think we've used millis as a way to measure time in the past. The micros command does the same thing, but instead of measuring in milliseconds in 1/1000th of a second units, micros measures in microsecond units, 1/1,000,000th of a unit, or 1/1,000,000th of a second units. So micros are going by really, really fast, but we need that because so are our pulses going by very, very fast. So what I'm saying right here is that when this code runs right here, it says, what time is it right now? Okay, and the time that we're at right now might be 1,000 microseconds. Okay, it comes in right here. Well, our last tick time, when was the last time this code executed, might have been at 500 milliseconds or microseconds. So our pulse time would be the difference between the last time we ran this routine and the time right now. And that tells us how long it took to go from rising edge to rising edge. And now what I do right here is I say, okay, I use that variable. Now I'm going to take the current time in microseconds, and I'm going to store that and remember it in this last tick time variable, so that the next time I hit that rising edge and come in here, then I'll have that displayed. And I use my serial prints right in here to display this. So if I run the code again, and I'm just going to turn off debug mode right there. I'm going to start, I'll show you a little bit more about debug mode in a moment. It's kind of cool. But if I start that simulation, I can bring up the serial monitor down here at the bottom. And what you'll see coming through right here, let me stop the simulation so we can see what's going on right here, is you can see that the number of ticks is increasing, and it's not increasing one at a time. I'll explain that in just a moment, but you can also see the last pulse time. It says it took 12,000 microseconds, which is 1.2 milliseconds. Okay, then it got a little bit faster, it got a little bit faster, and down here we're down to 7,500 microseconds, which is 7.5 milliseconds. And so if I run this again, you'll see that right here we've got this big long delay, and we've got big numbers on our pulse time. And as our pulse time delay comes down here, now you can see that we're 1, 2, 3, about 3.5 milliseconds. And right here we're showing 3,500 microseconds, which we're reading the same time down here that we're seeing the pulse time right up here. Down here we're down to about 2,000 microseconds, and on the screen we're seeing that from rising edge to rising edge, we're just under these 2 ticks, which are 1 millisecond a piece, or 1,000 microseconds a piece. We know that they're that because this is our scale that shows us we're 10 milliseconds all the way across the bottom of the oscilloscope, and we've got 10 units coming across right in here. So we're counting the number of ticks that the motor is going past, and we're showing how long each of them takes, and bang, we just slowed the motor down, and our pulse time went back up through the roof again. So does that touch on some of what's happening right in here?
Yep.
Okay. Now, for some of your coding, you don't have to calculate the speed of the motor, but I included this right in here because what this number right in here is telling us is an indication of the motor speed. The less time it takes to go from this edge to this edge, the less time it takes for that disc to spin around and put a new slot in front of the sensor, the faster the motor's spinning. So right here, we've got distance coming up in this column, how many ticks we've seen, and speed coming up in this column. The smaller the number indicates the motor spinning faster.
And Jason, for each pulse, is that one revolution of the motor?
No. So it's going to, depend on the encoder that you have on the back. So some encoders will be 10 ticks per revolution. Some will be 20 ticks per revolution. Yeah, some will be 200 ticks per revolution. But keeping in mind that this motor is a gear motor right here, and what we see on the output shaft right here is slightly dissociated from what we see on the back, because we can change the gearing on this motor. So if I right click on the motor, you can see you get this option to change the RPM. You're not actually changing the speed of the motor, you're changing the gear ratio in this gearbox. So if I tell it to, I want a 32 RPM motor, you can see my pulses here are still pulsing just as quick because the motor's flying at high speed, but the output shaft of the geared end of the motor has slowed down. And that's because what we've done is we haven't changed anything about the motor itself, we've changed the gear reduction inside here. So this would be spinning with a lot more torque. If I change it up to 624 RPM, okay, as a maximum speed, now it's spinning a lot faster. The motor's going at the same speed, but I've got less gear reduction, so I've got less torque coming out of my output shaft. So if we had a slightly three-dimensional view of that motor, it would make total sense. I have, oh, hold on just a minute. I can show you exactly what I'm talking about. I am going to plug a video camera in right here, and I am going to get bold and try showing video. And let's see. This is going to be very exciting if it works. So let's see. Somewhere on Zoom right here, I have settings right here and start video. And hello, can you see me?
Yeah, there you go.
Okay, hi. I need to get one of those funky Zoom backgrounds in here, but this is the type of motor that we're actually looking at right here. And this one's got a magnetic encoder on the back. So instead of having an actual disc flying around right in here, this little wheel that I'm spinning with my hand or with my finger right here actually has magnetic poles embedded in it. And this little sensor right here is a Hall effect sensor. And the Hall effect sensor, maybe I can, oh, hold on just a minute. I've got my, don't mean to induce motion sickness or anything right here. Does that show up a little bit better?
Yeah, that's good.
Okay, so right here, we've got that disc spinning around. Now, on a lot of encoders, this would actually be just a flat plastic disc or metal disc with holes punched in it around the perimeter. And instead of having a Hall effect magnetic sensor right in here, what you'd have is you'd have an LED light source on one side and photo diodes or phototransistors on the other side reading that. And on this motor right here, you can see that we've got 6 wires coming out of the back of it, and there's actually a little printed circuit board on the back. And just as our motor in TinkerCAD is hooked up and has power and ground for the motor, and then we've got power and ground for, in TinkerCAD, it's an LED, and here it's for the Hall effect sensor, which is a lower voltage, lower current signal. And then we've also got output A and output B, and I'll talk about the importance of those having 2 outputs in just a moment. But you can see in here that we've got the sensor on the back that's hooked up to the motor shaft, and then in here you can see that actually on this one,
Jason, you're just a bit out of frame on the
oh, sorry,
webcam.
Thank you. I can't look at this and my screen at the same time,
Yeah.
But I thought the light would come in handy down here. So you can you see the motor shaft right now?
Yep, that's good.
Okay, so the motor shaft comes in here, and in this case, it would be a spur gear that it's driving. So a small, tiny gear connected to the motor shaft, connected to a larger gear on a drive shaft in here, and then would come back and drive another gear on this side. So we've got a slightly offset output shaft. in our motor that we're looking at, it's a planetary gear set, kind of like cordless drills would have, so it comes right out the very middle. But we're looking at a shaft that is physically separate from the motor because we've got a gearbox in the middle, and that's how we're able to change the gear speed. So for any given encoder, you are going to have a fixed number of pulses per revolution. But for a gear motor, if you change the gear ratio, you're going to have a different speed coming out here for pulses right in here. So we need to be able to use TinkerCAD to figure out at a given speed how many pulses per revolution we're getting. And I'll show you a trick that we can use to do that right now. So does that just sort of give you a bit of background information on what that motor actually looks like? Because we're only seeing it in 2D right there. Okay, let's, I'll stop the video for now. There we go. Everything else is still working okay, I think. And let's take a look right over here. So right now, we've got this is our output shaft spinning around right here. And we'd like to know how many pulses does it take to do a revolution. So let's pick a particular gear ratio right here. And, we'll say 520 RPM. And we want to know how many pulses does it take to go around one time at 520. So what I'm going to do is I'm just going to stop the simulation right here. And really for this, we don't need the oscilloscope or even the timing right on here. What we're mainly concerned about is the number of ticks. And so if you've got the serial print right in here, and each time you come around, you're doing a print of the encoder ticks, you can start the simulation and you can say, okay, my motor is sitting right about right there, and go start simulation. And the motor comes around. I'm holding my mouse right here and I'm waiting for it to come around, and we'll say, let's count 10 revolutions. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then stop the simulation. And that was just about 10 revolutions. I was a little bit off right there, but that's why I did 10 revolutions. Is any error that we have, we can kind of average out. And you can see that this has been keeping track of the number of ticks. So when we were at about 10 revolutions, this showed us as being at 2,108 E3. It should have been a little bit more than that. Let's say it was supposed to be at 2,200 ticks at 10 revolutions. That would mean that we're getting about 220 ticks at the motor per revolution of the output shaft at this gear ratio. So what I can do now is I can say, okay, well, let's take a look right here. And while we're running this, I am going to come in here. I guess I'll put it at the end of the program, and I can put an if statement. If bracket ticks is greater than 2200, okay, then digital write, and I set right up here, I set, where did I turn my motor on? Oh, I was doing an analog write of 5,0. Then what
Have we called something ticks before? Like, does the code doesn't know just ticks?
Oh, sorry, encoder ticks. You're right. Thank you. Encoder ticks would have snarled at me if I tried to do that. Digital write brackets 5,0. Okay, and that 5, low. And that will turn the motor off. And then I can say else. So let me close off my brackets right here. Else analog write brackets. Am I in here? 5, comma, X. Oh, no, I don't want that right there. Pardon me, I forgot how I had my speed loop set up. I'm just going to get rid of my for loop right in here, because the for loop I just put in to speed the motor up and slow the motor down a little bit. Let me just come in here and set it if we don't want to mess around with the motor speed right now. I'm going to get rid of that for loop, get rid of that part right here, and I'm just going to start out with the motor on. So digital write 5, comma, high. So I'll set pin 5 high to start the motor turning in my setup routine. I'll come into my loop. Every time I run the loop, I will, I'll get rid of that. I don't want any speed control on the motor. I'll print out my information. I'll run a delay. And if the encoder ticks is greater than 2200, it will set that pin low and stop the motor. And we chose 2200 because we ran it 10 times, we printed out our results, and we divided what should have been about, 220, because we divided 2200 by 10. So let's start the simulation now. It initializes, it runs right here, and it stops right there. So we're kind of at the 11 o'clock point. I'll stop it. I'll run it again. Oh, we went a little bit past there. And now this is where this simulator is really awesome. Just going to stop this simulation here. And you see we're at 270 right now, but I told it to turn the motor off as soon as we got to 220. Well, just like when you're driving your car and you say, okay, hit the brakes at the intersection. If you hit the brakes at the intersection, what happens to the car?
Keeps going.
Keeps going right into the intersection. And you'll stop at some point in the middle of the intersection if you're lucky. Depends on how fast you're going. But this motor had enough momentum that it kept spinning until we got up to 270. So what we might need to do is actually hit the brakes a little bit sooner, or else run the motor at a slower speed. And if we start our simulation right now, that was a little closer to 1 revolution. And you can see here we stopped at 224. And I had to give it about 10% leeway in here to get it to stop in time. And this is one of the reasons why I really like robotics as an educational activity, because if you just do the coding part of it, you miss out on that whole reality aspect of momentum and all those nasty little things that come along that make your life challenging when you're working in the real world. So I'm just going to stop right there. So simplified the code a little bit here. I'll just walk through it one more time. We define some variables up here at the beginning. Encoder ticks is going to be used to keep track of how far the motor has turned. Okay, last tick time is going to, when did the last interrupt happen? Okay, and pulse time is the time between interrupts. Okay, and then we come into our setup. We set our Arduino pins to outputs. These control the L293D. Okay, so they have to be outputs. These ones used to read the encoder. And serial begin, of course, gets us our output. This sets up our interrupt. And this one right here starts the motor. We come down here, we get our data being printed out right here. We have a delay in here just so that we don't swamp the serial monitor by sending it data continuously without taking a break. It does, because it takes time to send and process the data. You usually want to have a bit of a delay in your data stream so that everything can catch up. And then we just check right here and we say, well, how far has the motor turned? And we stop a little bit early. One. Okay, and this command right here stops the motor. Okay, and this code down here runs and so that will run right in here. And then this is the code that measures the time of how long it took something to occur and then sets us up so that the next time a pulse occurs, we can see what's happening right in there. So that gets us 1 revolution. And if I was to double that, well, if I was to double 220, and it seems to take 20 units to stop, so I'm going to say 220 times 2 would be 440, subtract 20, I'm going to try 420, which was yesterday. And exactly, there we stopped. Oh, pretty close. We went a little bit past it again. Let's run that again. And 2 revolutions. And you see it doesn't always stop exactly at the same number of pulses because you know, the motor is a physical thing. Part of what's happening there is that the motor doesn't come up to speed immediately either. So if we start this, and I'm just going to hit start here and then stop it right away. Oh, I stopped it too soon. Okay, and what you see happening right down in here is that as we get up and we start running, some of our, I didn't leave it quite long enough in there. There we go, right in there. Some of our pulse times right in here, it takes a little while for them to balance out. And I was actually expecting them to be a little bit longer at the beginning and then slow down because it should take a while for the motor to accelerate. But what we may be seeing in right here is that the motor accelerates until the gears engage because you've got backlash in the gearing out here too. And if they're simulating that as well, they're just, you know, I'm blown away one more step by what TinkerCAD's doing because they've really thought through how a real motor behaves. You'd start with your motor on the backside spinning really fast because there'd be no load on it. And then the gears would engage in here because you've got that little bit of mechanical backlash in your gearbox. And then the motor would load down and slow down a little bit as it brings that up to speed. Let's just watch that progression. Oh, just a minute, stop the simulation. Start the simulation here. And there, yeah, now our pulse time got out to 13 milliseconds, 13,000 microseconds. So it gets steady right in here. And then let's run that again all the way through. And oops, I didn't stop that quite soon enough. 1, 2, sorry, I wanted it to come to a full stop right in there. And if I stop it right here, then you can see for our pulses, we're stuck right here at 486, 486. But as we came in there, we saw a couple in here where the pulses got a bit longer as the motor was slowing down. Then it just became fixed and constant because we weren't getting any more pulses. We kept printing them out, but we weren't incrementing anything. So nothing changed. So, so there's some neat stuff going on in the background in this simulation. And so sometimes if it doesn't work beautifully like you see in code, that's actually an extremely awesome example of how these things really behave in real life. Let me show you one other thing. We haven't talked in any of the videos about the debug function in here. And the debug function is actually kind of neat. And it might help us see a little bit more about what's going on in the program. And so when you click on debug right in here, you can add these things called breakpoints. And if I click on, actually, you know what? I'm just going to turn on all of our breakpoints right here. It'll be a little bit annoying. So every time I turn on, I only need it where I've got lines of code. I don't need that. Every time I turn this on, it's going to stop and ask for permission to continue the code whenever it comes to one of these lines marked in blue. And by doing that, we're going to be able to watch the progression of our code. So we will start the simulation, and you can see that right now it has stopped our simulation right here. And we can hover over variables, and when you put your mouse over top of them, you can see what each variable is reading. So it's kind of cool. And then we can click this little button right here. This one will resume automatically. This one will step. Okay, this one goes to the next command, the next command, the next command, the next command. It's setting it all up. Okay, it attaches the interrupt. And now we're out of setup, so our program is going to start working. The motor should start turning. We're going to print the number of ticks. Okay, and that should show up on our serial monitor. That should have come out and said 0. There we go. It just took a second for that to appear right there. So now we've had a brief delay in here, and let's keep going with our steps. We come back up to the program because our if didn't execute, so there was nothing else in here. We come back up here, and we keep coming around, and it's going to take a few and you see all of a sudden we jumped out of what we were doing and we came right down to here because we've just seen our first tick. And over here on the oscilloscope, if I'm able to move this up, you'll notice that we just went high all of a sudden right in there. And so let me just keep coming along right here. That comes through. This process is what we're doing. Our last tick time is 0 because that was when we started the program. And right now it is going to come in here, and last tick time is going to record our current time in microseconds. Okay, and our current time in microseconds was 10,000 microseconds. And looks like we're in the interrupt again. Last tick time equals going to update. We were at 10,000. So now our pulse time is our current micros minus that 10,000 that we recorded last time. So we'll take one more step into here. And now we've got a last tick time. That's been updated to 10,000 from 10,000, from 101,000, I guess, to 102,000. Now you'll see we jumped out of here because there's no interrupt occurring right at this time. We're able to come back in here, run a little bit of our regular code. Our regular code's running right in here. And at some point during this long delay, it's going to stop, bounce down right here. So our delay actually gets interrupted at like 20 milliseconds into the delay. It comes down here and runs this code. And because it's taking us about 1 millisecond to get each of those pulses, we keep looping around in here. Well, every time we do that, we're actually flicking back, and that delay keeps incrementing right in here. So this code is running right in the middle of this delay. It's like there's two things going on at the same time. But because one of them's interrupt controlled, there we go. That's pulse through right there. And we just saw that go low on the oscilloscope, so it should in a moment. Oh, it was just waiting for a new pulse to come in because we were running so slow. We should eventually kick out of here. And lots of pulses were happening behind the scenes that we didn't even see during the middle of that delay. And then once we've looped through here a whole bunch of times, let's execute that. Does that step over the next function? No, there we go. And there we kicked out of the interrupt. We came back in here, we executed this code, got back into the delay loop, and now we're right down here. So our interrupts are actually powerful enough to break right into the middle of that delay and kick us out.
And for the fact that it's going in the middle of the delay, does that make it less accurate, or is the timer still going?
The timer's still running. The timer runs in the background.
Right, so the delay is still 50 milliseconds.
The delay is still 50 milliseconds.
Okay.
Yeah. And now, this is also a place where you run into some real problems with encoding interrupt-driven routines. Is if that delay occurred in the middle of your interrupt, or if your interrupt took longer to process than it did to go from one rising edge to the next rising edge, then your code would trigger a new interrupt in the middle of your existing interrupt. And it would say, okay, remember that I have to come back and run line 31 or line 32, whatever. It would jump over here to the interrupt, and it would start processing the new interrupt before it had finished processing the previous interrupt. And then you'd trigger another interrupt while you were still in this interrupt routine, and it would start processing that one before it would finish the last one. And it's kind of like, yeah, you know, when you get 50 homework assignments in 30 minutes, and you know you can't get one done because the next one's coming along too soon, and eventually it just all goes to hell in a handbasket. So that's what's going to happen if you get stuck in there and your interrupt is too long. So interrupt handlers need to be really, really fast. So I don't know if that gives a few ideas about what's going on inside this code and a few ways to track it out. This is about as deep a dive as I want to do into what's going on, you know, internally within the chip. There's some neat stuff that's going on. You can also trigger interrupts using internal timers. And that's what like the servo library and even the pulse width modulation function for the analog write, they're using internal timers to generate interrupts. So they're actually using this technique to break out of your code, do their thing, and then give your code control. And it's almost like they're running in the background, but if you were able to watch them at super high speed, you'd be able to see your code stopping and going and executing an interrupt handler and then coming back to your code because of the libraries that you're using.
Yeah, this has been helpful. Like even watching you in the setup, set it high, which means turning it on, like even that makes a click in my head, like realizing what the setup means, what the loop means, like every little thing is helpful for sure.
Yeah, well, I'm glad, you know, this is one of the good things about, you know, the meetings that I've had. I've really enjoyed talking to everybody one-on-one this week, and it's given me enough confidence with Zoom to say, well, let's try something like this. And you know, it's not a good replacement for being there in class and being able to, you know, talk to each other as we're doing this hands-on. But under the circumstances, it might be the best replacement that we've got. And certainly the ability to take this and share it and say, oh, fast forward to the, you know, 5-minute part where Jason stops rambling or something like that will be helpful. So maybe what we'll do with a couple of the other programming challenges people are getting stuck, we'll, you know, be able to schedule another meeting next week. One thing I did want to mention that I am going to be taking a look at because people have told me that they quite like it is I'm actually just going to turn the code off right here and bring up a new TinkerCAD window. Is this still displaying?
Yep, we can still see what you're doing.
Okay, so I'm logging into TinkerCAD right here, and I'm just going to create a new code block right in here. And that's not what I wanted. What did I click on? Oh, this is something entirely. Is that just regular Tinker? Back to the dashboard. Code blocks. Oh, that is new. That's something. I want a new circuit. I have no idea what the code block is. May have to explore that in more detail. Circuits. There we go. Create new circuit. And so when you come to your code right here, oh, okay, it needs something programmable in there. Just a minute. So let's come in here and drop our Arduino in. And then let's come to our code right here. And I've completely been neglecting to talk about the block-based programming. And thankfully, a few people have gone and started exploring this on their own and said, hey, this actually works really well for me, because if you're not into semicolons and capitalization and squiggly brackets versus round brackets versus square brackets, this takes care of a lot of that for you. And what I particularly like is the blocks plus text option right here, because it shows you by dragging the blocks on here what you get in text. So this command right here, set built-in LED to high, translates directly to digital write 13, high, and it puts it in the void loop. And because you're using that as a digital write down here, it says, oh, well, you better set that to be an output, and it drops that in your setup for you. And if you come in here, you can put, where are we in here? Under your control, you can put something like repeat 10 times, and then you can drag this code and put it right inside there. And so your repeat 10 times gives you the for loop right here, that it creates a variable called counter to keep track of this. It starts it at 0, keeps doing it as long as it's less than 10, increments it by 1 each time it goes around. And now we've got this code right in the middle. Well, here it's wrapped by this orange shape. In here, it's wrapped by these two squiggly brackets. The orange shape represents the squiggly brackets right here. And so, if you bring in an if statement right in here, now we've got if, and it brings in the squigglies because that's right in there. And then you can come to your outputs and, set, well, digital write 0, high, and you say, oh, geez, I meant for that to be an if then else statement. Well, you drag that right in there, drag that down in there, throw that away, pop that in right there, and it does it all with kind of cool little sound effects. And then you can set, oh, I wanted it to go low, and you can see it changing the code over on this side as you go ahead and write it. So if you're a graphically oriented person, this is kind of cool. And I'm going to be taking a look at some programs like Scratch and VexCode VR that use this approach. But I like the tie-in right here that it gives us, where you can see this appear as you come along and type. The downside to it is that you don't have as many commands. And so we don't have, we had to do that set up, and we had to say pin mode input underscore pull up. There's no input underscore pull up option in here because that's just a little bit more complex than what they can handle with their drag and drop blocks, or they don't have it set up just yet. But there is some cool stuff that comes right in here that you can explore using the drag and drop. And for some people, it's going to be a lot quicker way to create the code. We've been on here for an hour or so. I hope that's been helpful. I'm happy to answer questions.
Yeah, it's been helpful having you walk through all that and talk about all the different aspects of the Arduino and how it relates. It's for me, because I don't know, maybe it's because I've used a hammer to bang nails for the past 8 years, but I still find like it's trying to understand a completely different language. And even though with the amount of time that you and I have spent on it in the class time, I still look at writing code and I just yeah, I don't know. That's why I'm here.
Yeah, exactly. And you know what? It's not one of those things where our goal is to have Electronic Arts or Microsoft come and hire all our graduates. We're not an electrical engineering or a computer science program.
Thank God.
Our goal is to get you enough knowledge so that if somebody comes out and they say, hey, we've got 2 blocks of woodwork, we want you to start a carpentry program, but the guy who's retiring left up 1 block of robotics or 1 block of computer science, can you come, or not IT or whatever they call it these days, can you come in and can you handle some of that? Or if you get called in to, substitute for somebody's class, or on your practicum, there's, something in school going on. We just want to make sure that you're familiar with some of the general concepts, that if you ever have to present a lesson on it, you're not starting from zero. You can fake a lot of knowledge if you've got a starting point, and you can go home the night before and say, okay, right, what did we do? Okay, I got to teach a lesson on Arduinos tomorrow. I've got a couple of videos recorded on TinkerCAD. I know how to solve this one problem. I'll teach the students how to do the one problem that I know. And so if we can give you that, then that's a good start. And for some people, actually, we find that they come in thinking, oh, I'll never get a hang of this coding, and they discover, why haven't I been doing this my whole life? I'm good at it. Different levels of success for different people, but I think we get everybody up to the point where you can leave here saying, I can make these microcontrollers do useful things for me. And, maybe I have to work at it a little bit hard, but if it's one of those things, you can't imagine what they can do unless you've got some concept of what they can do. And as much as anything, I want to inspire that imagination, so that if you're building something in the wood shop and a kid says, I'd like to have lights that when I open the door, they turn on, but I want them to fade in slowly. Okay. And you can sit there and say, I have an idea on how to do that. And, I'm not going to sit down and wing it, out of thin air, but here's some things that you should look at. You're looking for Arduinos, and, to fade an LED, we used pulse width modulation. So take up a look at Arduino LED pulse width modulation, and they'll come to the analog write command. And if they want to make it happen, you'll have just directed them to the right resources. So, we're just trying to enable a few things with that, I think.
Yeah, pass on your phone number to the student.
Actually, I quite often get emails from recent graduates who are out there. They're doing something interesting, and they're just like, hey, I remember you did this. I just need a couple of keywords, or I need a handout that I forgot to save. Or can you give me a quick hand with that? And I like to think of that as after-sales service and support. It's a very important part of the technology industry. Absolutely. And so your diploma doesn't come to an end the day we kick you out the door. And as you get into the teaching profession, I certainly hope everybody knows more about their subject area 5 and 10 years into their teaching career than when they come out the door of BCIT. And for some of you, it's going to be the woodwork or the auto mechanics or whatever you dreamed about teaching when you came into the program. And in other cases, you're going to be off on some grand exploration of robotics or electronics, or integrating things together. And you're going to be 10 years from now, you're going to be having people come to you like saying, oh, well, you're the expert on this because you've been doing it. And you're like, no, you don't understand. I never meant to get into this field. It's just sort of worked out that way, and I'm having a good time and I'm rolling with it. So you never know where this career is going to take you. So we try to provide you a little bit of preparation for wherever it might go. You guys feeling time for some lunch now, or?
Yeah, exactly.
Okay.
Yeah, around there.
Well, I will figure out what to do with this recorded file here so that I can share it with you somehow.
Yep.
and then we'll be in touch going forward.
Thanks a lot,
Great.
Jason.
Thank you so much for your time, Jason.
Thanks,
Really
Jason.
appreciate it.
Hey, no worries. That's what I'm here for. Okay, stop share and stop recording.